So let me recall the point where we stopped yesterday, which was on this question. This is maybe here. So, which was how to put and now I say reasonable after a discussion that I had with one yesterday, probability distribution on the space of polynomials. And remember I said that it's a vector space. Of course, this is something like R, and maybe let's say R m plus 1. So it's just some vector space of some dimension. And I wanted to put a Gaussian distribution on this space. That was my goal. And just recall that, so imagine like a Gaussian distribution on a vector space V, as I explained, if it is non-degenerate, that we can denote it gamma V, it's going to be a probability distribution written in this way. There is some constant, and then we integrate on E, function of the type some norm squared with respect to Lebesgue measure. Okay? And it doesn't have to be, so when you write some norm square, if you want, you can choose the Euclidean norm, and then it's going to be something like this, where A is a positive definite matrix. Okay? So that's the way you can write Gaussian distributions. If you don't feel comfortable with this description, just imagine that this matrix A, or rather its inverse also, defines a sphere in my space. Okay? So this would be the set of points where okay? It's not the round sphere, so maybe this is the round sphere, so let's say, and maybe let me use another color, because otherwise, so when I pick A, okay, maybe it has another shape, okay, but it's still an ellipsoid. And essentially, it will be the reference sphere with respect to which we want to work. Okay, so that's the idea. And it's always possible to turn this into the standard distribution. I mean, writing an isomorphism with some Rn with the standard Gaussian measure, which is what I defined. And it's just you choose an orthonormal basis let's say V1, Vn for the chosen scalar product, and you define the map, say that sends Vi to Ei. That's a standard basis in Rn, and this map push forwards your measure into this measure. So just a way to give appropriate coordinates on your space. Okay? So, see, now let me go back to our problem. I want to put a Gaussian measure on my space, but I want it to have a reasonable, or I say natural, but maybe someone objects it's a cultural choice. But let me tell what is, at least for me, natural or reasonable. So here there is a group acting on my space. This is what we were discussing yesterday. Okay, and this is the action by change of variables. Okay, so you take, as I said, a matrix G, and you have this row of G, and row of G of a polynomial P is just P composed G minus 1. So it's a representation of the orthogonal group into the space of polynomials. If you want to have an example, maybe, when the degree is 2, the space of polynomials is isomorphic to the space of symmetric matrices. By the way, for this isomorphism, you also need to choose a scalar product, but let's say with respect to the standard scalar product in Rn, and the isomorphism is basically to Q you associate the symmetric matrix Q, which has the property that Q of X is X transpose Qx. Okay, so it's a polarization. Now in this case, the action by change of variables is just the action on the right-hand side that sends Q to G transpose QG. Okay, so just acting by congruence on your matrix. Okay, this is the action if you want to visualize it. And you see already in the case, so D equals 2 and N equals 1, so 2 by 2 symmetric matrices. What does this action do? So 2 by 2 symmetric matrices, it's a three-dimensional space. And the action, so if this is the multiple of the identity, the action is just rotation along this axis. Okay, so the group O2, or SO2 rather in this case, acts on the space of polynomials of degree 2 in two variables in this way. So multiples of norm of x squared are left fixed, and you just rotate on its orthogonal complement. Now already from this picture you see that if you want to put a scalar product on this space which is invariant under the action of this group, there is a lot of freedom. It's like asking you, can you put an ellipsoid in this space which is invariant by this action? Of course, every rotational invariant ellipsoid will play the game. And every such rotational invariant ellipsoid will give us an invariant scalar product. Okay? And as we go to the case of polynomials of degree D, not just degree 2, degree D, the situation becomes increasingly more complicated. Not that much. So in this case, you have one parameter, essentially, as a degree of freedom. And in degree D, you're going to have D choose 2 parameters, let's say. Okay, so D choose 2 plus 1 parameters. I will tell you this with more details in the next lecture. But just be aware that here we have to make a choice. Okay, so if I want to put a Gaussian measure on the space of polynomials, and if I want this Gaussian measure to have some invariance property with respect to this action, I have to make a choice. Okay? On the set of linear polynomials, every choice you make, if it is reasonable, it's going to give you the uniform measure on the space of, so the standard Gaussian measure on Rn, space of linear polynomials. Just because the action by change of variable, it's transitive on the unit sphere. But in this case, there are choices. And now there is really something cultural here, which I believe, which is there is a theme which is comparing real world with complex world. I think this is really, as I said, a cultural thing, like at least in this audience. I want to make a choice now at this point, which has which is meaningful when comparing R with C. Okay? So I'm going to now give you the choice of probability distribution, which means I'm going to tell you which scalar product I'm going to pick on my space of polynomials, based on the fact that later on I would like to compare real algebraic geometry with complex algebraic geometry. Okay? So this is how I make the choice now. And now comes the interesting thing. If you look at the same picture over the complex numbers, you take the representation of the unitary group, which I denoted this way, okay, into the space of complex polynomials, okay? So this representation is irreducible. This is not. And here is an example, of course. There is a proper invariant subspace, that's the multiple of the identities. Okay? And by the way, just again to let your brain acquainted, the irreducible decomposition of this representation involves spherical harmonics. Okay? So a generalization of that picture over there. But in this case, it's irreducible. That means that if you want to put a Hermitian scalar product on this space, which is invariant under the action of un plus 1, so if you want to solve the same problem, how to find now not a real, but some Hermitian product, by sure lemma, you only have one choice. Okay, so sure lemma implies that there exists a unique Hermitian structure on this space, on the space of polynomials, which is, let's write it this way, un plus 1 invariant. So for which action by change of variables with unitary transformation are isometries of this space. And I'm going to tell you what is this structure. It's a definition. It's called the Bombier-Rivale scalar product or Hermitian structure. And it's defined in this way. So I give you two polynomials, say P and Q. These are complex polynomials, homogeneous of degree D in n plus 1 variables. And I need to define their Hermitian product, which I denoted this way. Okay, so several options, all equivalent, but just maybe one that I like is the following one. You integrate on Cn plus 1, first polynomial times the complex conjugate of the second one, and you integrate it with respect to this, again, Gaussian measure. Okay, so this is the definition of the so-called Bombier-Rivale Hermitian structure. Of course, playing a role which is just again by this sort of like passing to polar coordinates, this it is the same, so up to constant, maybe it's a remark, that up to constants, this is the same as up to constant, integrating on the complex, so on the sphere inside Cn plus 1, the unit sphere, just P times Q bar with respect to the volume measure of the sphere. Okay? Because you can just pass to polar coordinates over there. The polynomials are homogeneous, and you just get this description. There is a little bit to play for this constant. But from this description, you see that this is unitary invariant. Because if you act with the unitary transformation by change of variables on each of these separately, what you get is that you just change, you apply the change of variable formula, the minus norm of z squared, it's transformed by unitary transformation, which is preserved, so the measure is preserved. I think this is more visual. Okay? You just act with the unitary transformation on the sphere S2n plus 1. You rotate the sphere with some unitary transformation. You preserve the measure, and this integral gives the same value. Okay? After you apply this. And because the representation is irreducible, this scalar product is the unique invariant one. The Hermitian structure is the unique invariant Hermitian structure up to multiples. Something nice about this Hermitian structure is the following. Here is an orthonormal basis, Hermitian orthonormal basis. I call it maybe B and D. It's this. So you take the monomials, but you have to scale them by this square root of a multinomial coefficient. So this is an Hermitian orthonormal basis for the Bombieri-Weil scalar product. Look at this basis. It's a real basis. Okay? So you can now restrict the Hermitian structure to, take the real part of the Hermitian structure and restrict it to the space of real polynomials. You will get a scalar product on the space of real polynomials, for which this basis is an orthonormal basis. Okay, so the Bombieri-Weil scalar product on the space of polynomial, I denote it the same way. I take two polynomials, the Bombieri-Weil, these are now real. It's up to constant again, it's this integral. You don't have to take, well, you just have to conjugate the variable if you want. On the sphere. Or said it differently, it's the scalar product on the space of real polynomials, which has the property that an orthonormal basis is the following, is this scaled monomial basis. And because the orthogonal group is a subgroup of the unitary group, this scalar product is orthogonal invariant. Okay, so this is the construction. So we have made a choice of a scalar product, and of course I'm going to build a Gaussian distribution feeding to that formula this scalar product, and I'm going to get a Gaussian distribution on the space of polynomials, which is invariant by orthogonal change of variables. What is special about this Gaussian distribution? It's, if you want, the restriction of the analog construction over the complex numbers, which is characterized by uniqueness. But over the reals, there are other possibilities. For instance, here is another example which I put with a different color so that you remember. For instance, here, you could take a scalar product between P and Q. Here is another choice. I denoted L2 Sn. You could just take integral on the real sphere. This is another choice. This is also orthogonal invariant, but on the space of polynomials, it induces another scalar product. Okay? In this picture, it means just shifting, if you want, from one sphere to another sphere, to an ellipsoid. Okay, this choice. And so finally, my definition here, it is the following, that the Bombieri-Weil Hermitian structure, the Bombieri-Weil probability distribution is the following. So I denote gamma BW. This is the probability distribution on the space of polynomials induced by the Bombieri-Weil scalar product. Okay? And for the rest of the course, I'm just going to think about this probability distribution. Okay? So if you want, I've chosen a reference sphere inside my space of polynomials. And whenever I'm going to measure some set in my space of polynomials, if it is a cone, I just need to measure the volume that this set takes in the sphere with respect to the Bombieri-Weil scalar product. And this will be good because it allows comparisons with complex algebraic geometry. Okay. So let me start maybe. So this is the framework, the setup. Okay, now we have put some probability distributions on some parameter spaces, Grassmannians, okay, orthogonal groups, projective spaces, which are special cases, spheres. On all of these, there was a natural choice. On space of polynomials, that's another choice that we made. This is dictated by the cultural comparison of R with C. And now let's start doing something. Let's start asking some questions and see some tools for answering this question. So you see, as we were saying yesterday, now we have our space of polynomials. Now, if I'm interested in, for instance, and maybe I do the same picture here, and now for every polynomial, I can look at like its zero set. Okay, it's something like this. Now this zero set changes on the space of polynomials when we cross some discriminant, but now we also have a measure. So now we can measure the size of the regions where we have a given zero set. Or another thing we can do, we can integrate functions on this space. This would give the average value. And of course, again, keep in mind the same answer over the complex numbers will just give you back the generic answer. So here is a tool which is quite useful and I think very important in this subject, which allows to compare the notion of degree from complex algebraic geometry with the notion of volume from real algebraic geometry. Okay? So in some sense, you should keep in mind that when you pass from complex algebraic geometry to real algebraic geometry, you should not think really about degree, but volume. And over complex algebraic geometry, these two things, degree and volume, they are synonymous. And that's what I want to show you now. Okay? So the tool that will allow us to do computations is the following. It's called the integral geometry formula. It's very beautiful and has nothing to do with, at this point, with this discussion, and it's the following. So pick two submanifold in the sphere, in RP, let's work with projective space, in RPN. These are just smooth submanifolds. Say that A has dimension A, and B has dimension B, and so I call C n minus A minus n minus B. So that's the so it's the codimension of the expected codimension of an intersection of these two manifolds. Just a number, keep it here, okay? Don't worry. Now we can do this game. I can take A and I can intersect it with GB, where G is an element of the orthogonal group. Sorry. So now this intersection for most of the elements of the orthogonal group is going to have dimension C. So it's a manifold also. I'm going to take its volume and normalize it by the volume of the projective space of this dimension. So you can consider this. So for instance, if A and B have complementary dimensions, I'm just integrating on the orthogonal group the number of points of intersection between A and a rotation of B. And the integral geometry formula writes this integral in a closed form, which depends just on the geometry of A and B. And more precisely, it's just volume of A divided the volume of projective space of dimension A times the volume of B divided by the volume of projective space of dimension of B. So for example, let me draw this example. So here is RP2, and I pick A to be just a curve if you want. Okay. And for B, I pick an RP1. Okay. Now let's apply this formula that I wrote here in this specific case. So let me integrate on the orthogonal group O3, sorry. So now this has dimension 1, this has dimension 1, so the expected intersection has dimension 0. So volume in this case means 0-dimensional volume, so number of points. Volume of RP0 is 1, volume of 1 point. So I'm integrating the cardinality of A intersected with this line, G RP1. Okay. And the answer is, well, volume of A divided by the volume of RP1, so it's the length of A divided by the length of RP1, which is half the length of the sphere S1. It's half the volume of the sphere. Projective space is induced with the quotient metric, okay? So, and the density locally is the same, but you're integrating Euclidean, standard Euclidean sphere, yeah.
And is it the same that the one is used by
There is no BW in this picture yet, R1. It's but there is no, so if you put a scalar product on the space, on some Euclidean space, you take the unit sphere, take its okay, you get some volume form. This volume form actually is invariant by antipodal map, and it's a lift of a volume form on the projective volume density on projective space. You integrate, you get just 1/2 the volume of on projective space what you get on the sphere. Okay. It's the same thing as, but no, if you push it forward, you get twice, right? But here it's just you just take the induced Riemannian volume from the metric. But the one thing that I wanted to stress about this formula, so here is what we are doing. We are, acting with the orthogonal group. We are rotating this RP1, okay? And you see, we're just averaging the number of points of intersection as we let this RP1 vary, okay, using the orthogonal group G. But that's, if you remember what was my definition of the uniform distribution on the Grassmannian, it was precisely the one induced by the orthogonal group, okay? So I can also write this in this way. It's the expectation over just a line on the Grassmannian of lines in P2, okay, with the uniform distribution of the cardinality of points between A and my line, okay? I've just written the same thing with the language I introduced yesterday of having a probability distribution on the Grassmannian. And my probability distribution was defined as the push forward of the action map through the orthogonal group. So that's why I can write this in this way. See, there is also a complex version of this formula, which is exactly the same, but where you replace everything, so orthogonal group with the unitary group, and A and B, instead of being smooth submanifolds of dimension A and B, are complex submanifolds of complex dimension A and complex dimension B. You get this formula, so if you integrate on the unitary group the volume of some, let me put it maybe this way, complex divided by complex projective space of dimension A, G complex dimension C. You integrate with respect to the uniform distribution on the unitary group. You're going to get the volume of these divided by the volume of CPA times the volume of these divided by the volume of CPB, where by CA and CB I just mean complex submanifolds. Okay, that's what I mean. Now take a look at this formula. Choose for A what I just wrote here. Choose for A now, so for CA, some complex hypersurface of degree D. And choose for B just some hyperplane in projective space. Apply this formula. This is what we get. Integral on the unitary group, cardinality, number of points of intersection between your hypersurface and a rotation of this Cpn minus 1 equals the volume of my hypersurface divided by the volume of Cpn minus 1. Then I would have a volume of Cpn minus 1 divided by Cpn minus 1, which is just 1 in this case. But what's on the left-hand side here? By definition of degree, this function, the integrand, is constant almost everywhere. It's a definition of degree. So this integral is D. Yes?
You take just y.
Sorry. You're right. Sorry, Slav. You're right. I'm just, I don't know why I'm thinking of the curve. Yes. Yeah, I'm just slicing with the line. Yes, of course. Okay. So this is definition of degree. I have an hypersurface. The degree is number of points of intersection with a generic line. Okay. So the integrand is constant almost everywhere. The unitary group is normalized to a volume 1, so this gives D on the left-hand side. On the right-hand side, we use the formula and we get the volume of the hypersurface divided by the volume of this. So you see, in the complex algebraic geometry, degree and volume up to this constant are the same thing. Yes?
Sorry. When the volume of A is equal to GB, how do you compute the volume?
See, of this object.
Yes.
So, good question. Maybe I was too fast. So I just say, okay, just to make. So this is for almost every G, the intersection is transversal.
Yes.
Okay. When it's transversal, then it's a submanifold. Let's put it this way. You restrict the volume form, okay, and then you compute the volume with respect to this. Okay, so that's the idea. Yes?
Does this work whenever A and B are singular?
Yes, it also works when they are singular, except, so let's put it this way. If it's irreducible, no problem. If it's, the formula also works if they are singular. You just have to be careful what you mean by volume. And again, you do the following. In fact, it works for whatever nicely stratified set. First of all, the formula only sees the strata of maximal dimension. Okay? And you take a stratification, okay? And up to measure 0, you can refine the stratification and blah, blah, blah. The only caveat here is that in the complex framework, you really have to work with complex analytic objects. Okay? So this formula, if you replace that these submanifolds are real submanifolds of complex projective space, it doesn't work. It only works for complex submanifolds of complex projective space. Okay? But not for real submanifolds. Yes? Sorry? It makes sense for real. Yeah, and it has been done. It's called the Hermitian integral geometry. And it depends. So you see, if you have a real submanifold of complex projective space, at one point you can take its tangent space. Okay? Then do this tangent space. Now take I times this tangent space. You get another space. If it was complex, it's the same space. We have two spaces of the same dimension. You can compute their so-called principal angles. They come in pairs, which are called Kähler angles. and the formula depends on the Kähler angles. Okay, it's some property of the submanifold. A totally real submanifold, for instance, would have Kähler angles pi over 2, some sort of Lagrangian submanifold, and instead, like a complex submanifold, have Kähler angles 0. So the submanifolds are complex. So it's a good comment because for what I plan to say, because if you look at this, if you stare at this formula, there is some general, look at it from very far away. There is a group acting on some homogeneous space, and there are submanifolds of some homogeneous space. It's a compact group, and you want to average some metric property of the intersection over the group action. The thing is that you cannot expect to have such a formula, such a pleasant formula in general. But if you restrict the class of submanifolds to which you apply, you work on, you can expect to have nicer formulas. In real projective space, because if essentially the stabilizer of the group action acts transitively on all Grassmannians, you don't have put restriction. In the complex projective space, you have to put restrictions. Okay? And maybe just keep in mind that if I have time, I'll just mention briefly what happens in Grassmannians, and you still can produce formulas like this, but you need to work with special submanifolds. And Schubert varieties belong to this class of special submanifolds for which you can get such a formula. Yes? No, I mean, yes, I mean, good point. So if, let me take P to be irreducible, okay? It's simpler, okay? If it's not irreducible, you have to change it a little bit to take into account the multiplicity. It's not the cardinality of intersection, but it's the sum over the point of intersections with multiplicity, okay? If it's irreducible, no problem. Almost every line, slice it like, but otherwise you have to just adapt it. Yes, thanks. Sorry? Yeah, I agree. That's a good point. But if you take a line squared, for instance, you have to, so it's perfectly smooth, okay, from the point of view of differential geometry, but it's singular in here. And you would want to get 2 here, so you have to integrate this with multiplicity. That's true, absolutely, yes. Good comment. So maybe another comment is that you can apply this formula also to prove the so-called BKK theorem, Bernstein-Khovansky-Kushner-Renko theorem. So if I have time, maybe I'll say a couple of words. But otherwise, you can look at the lecture notes where I wrote a proof of these using the complex integral geometry formula. And by the way, there are these lecture notes on my webpage. And I will appreciate if you find any mistakes or things which sounds false. Okay, so now let's take a couple of steps back. Let's look at that picture. I want to use this formula to start studying some properties of random polynomials. Okay, so some properties of the geometry of this Bombieri-Bile distribution in the space of polynomials. And yes?
Degree of the variety, it depends on where it is embedded. But with the formula that we have, this, based on the volume, to me at least, is not dependent on where it is embedded.
You mean the right-hand side?
Yes.
Yeah, that's a good question. And it might lead to something interesting. But certainly on the left-hand side, there is an embedding because you're acting with a unitary group. But it's true that this formula just sees the volume by just intrinsic thing. That's true. So maybe, I agree, it's strange in some sense. But I don't know if there is a way to look at it from a slightly different
And also, one thing with this formula, we can calculate the ideals at a complete intersection, I guess, with f1 to fn. If generated, then the degree of the variety is the multiplication of degree of f1.
Yes.
I think it's possible to see.
Absolutely. So I was going to say maybe a few words. With this formula or a slight variation, you can prove essentially Bézout theorem using this formula. Okay, and I'm going into this. Okay, So let me maybe set up the framework. So I want to take as a parameter space now real polynomials of degree d1 times real polynomials of degree dn. So that's my parameter space. Okay, it's a product. So an element in this space would be a list of homogeneous polynomials of degrees d1 up to the n. Okay. So now on my space, which is here, there is some. I can consider the set x, which is the zero set of these polynomials. Okay. It's a system of n equations in Pn of degrees d1 dn. Okay. So these, for the generic choice of polynomials, just consist of finitely many points. Okay. And it has a cardinality at most d1 times dn by Bezout theorem. Okay. So this means whenever the system is for generic P. Inside my space of parameters, there is some discriminant again, which is the set of systems which have a singular solution. Okay? And now we can, of course, if we work over the complex numbers, this has codimension 2 real, so the complement is connected. And now you have a function, right? Every point here, you can count the number of solutions. Let me call it this way. Okay? The number of solutions to this system. And the question is, can we compute the integral of this function with respect to the Bombier-Rievail distribution? Okay, so this means what is the expectation of the number of solutions of this system of random equations of degree d1 up to the n, where each polynomial is, I'm going to take the product measure here, by the way. Okay. And I want to compute this expectation. So if you take the special case d, so n equals 1, you just have one random polynomial on RP1. Okay, and you want to know what's the expectation of the number of real zeros with respect to the Bombier-Rievail measure. So it's the integral of the function number of zeros on this space. And the theorem, pretty beautiful, due to Edelman, Kostlan, Schub, and Zmail. It's 4 names because Edelman and Kostlan did it when the degrees are all the same, and Schub and Zmail when the degrees are different, is the following, pretty nice. It's the product of the degrees to the power 1/2. So a random, polynomial, Bombier-Rievail polynomial in one variable of degree d, on average has square root of d real roots. Okay? And I want to show you the proof of this, which uses the integral geometry. Okay? It's very beautiful, very nice, very geometric proof. And in fact, it combines, maybe I should get that blackboard down. This one. And at the same time, I'm going to put this up. Ah, no, you cannot do it simultaneously. Let's see. So at this point, if you have never seen this in your life, it should sound strange that the integral geometry formula can produce or can help proving this theorem. Okay? But it's actually quite easy to see the proof after you buy the integral geometry formula. If you believe it, then the proof is not complicated. And it involves a nice idea, which is essentially studying the geometry of the Veronese variety. So we do the following. Let me take, so I want to apply the integral geometry formula, but to a special, when I need to choose in an appropriate way the object I am intersecting. Okay, this is what I want to do. So consider the Veronese map. Okay, RP big N, where this big N is N plus D choose D minus 1. And of course, it's the projectivization of the dimension of the space of polynomials. And in this RPN, I have a natural way of labeling the coordinates using multi-indices. Okay. I mean, we usually label coordinates in projective space, homogeneous coordinate x0 up to xn, but you don't have to do this way. I'm just labeling now according to the dimension of the space of polynomials. Okay, all possible choices of multi-indices out of n elements with total sum d. Okay, just a way for labeling. Now, usually when you do Veronese map, you would take x0, xn, and you would send it to all, so evaluation of all possible monomials of degree d. Okay, this is a version of the Kodaira embedding. We do the same here, but not with all monomials. I mean, not with just the standard monomials, but we just shift with our multinomial coefficient. Okay, so in position alpha, we put evaluating this monomial on x0, xn. Okay, it's essentially up to a linear change of coordinates or multiplication of the monomial by this. It's the standard Veronese map. Okay. Someone might argue that even another version is taking power sums. Sorry. It's big N. Thanks here. Thanks. Another version of the Veronese map you would take is taking power dth power of linear forms. In some sense, that's what we're doing here. So what is good about the Veronese map? The following. Well, first of all, it's an embedding. Okay, it's an homeomorphism onto the image. Okay, and if I take a polynomial p, let's write it as sum of c alpha, some coefficient, times our basis element. Okay, this is a special way for writing. I'm just writing a polynomial in my basis. Okay, this is my basis. If you want to go back to your usual, just take these as the coefficients. Okay, it doesn't matter. So what is good about the Veronese embedding is the following: that if you take the zero set of your polynomial and you map it through the Veronese embedding in this big projective space, what you get is precisely the image of RPN, so the so-called Veronese surface, intersected with the linear plane given by sum of C alpha W alpha equals 0. It's an hyperplane. Okay, so this is a standard property of the Veronese embedding. It transforms the geometry of hypersurfaces of degree d into the geometry of hyperplane sections of the image under the Veronese embedding. Okay, this is the key point. Everything is here. So if you now have a bunch of polynomials, n, okay, same story. You get this list of coefficients. 1 alpha, W alpha equals 0. You get Cn alpha, W alpha equals 0. So this is now some r p big N minus little n. For the generic choice of the coefficients, these impose n independent equations on Rp big N. Okay? Good. We're getting close to what we want to do. Now, you see, when the number of solutions is finite, the cardinality of the zero set of P1, Pn, so the cardinality of our system, so the function we are studying on our space of polynomials, it's the same, because it's a homeomorphism, as the cardinality of the image. Right? This should be obvious. I'm just saying a bunch of points. Just see these points in this big space. Okay? It's a Veronese surface. So here is Pn. I'm feeding it inside my space. Here there is some polynomial. Here some hyperplane. And this number of points, 1, 2, 3, is the same as this number of points. Okay? Nothing changed, except the type of way you get this object is changing. Okay, so that means that the function that we want to integrate, which is the integral on our parameter space of this cardinality, it's just, I write it now again using this form notation, it's expectation of this cardinality. It is the expectation of the cardinality of this intersected with this. Intersected with this hyperplane. Let me call it maybe H, which of course depends on the coefficients, on the list of coefficients. Now here comes the good thing. Remember, the Bombieri-Weil distribution was chosen in a way that these coefficients were independent Gaussians. But then when we translate back to just looking at this equation defines just a uniform Rpn minus n, so a uniform element in the Grassmannian of n minus n planes in big N. So what I'm saying is the random coefficients were in the polynomial at the beginning. After we do the Veronese embedding, the random coefficients are no longer in the polynomial, are in the hyperplane, are in the linear spaces with which we intersect the Veronese. But this linear space now, because these are all independent Gaussians, is distributed as a uniform linear space in our Grassmannian. Why? Because the Gaussian distribution is orthogonally invariant. And on the Grassmannian, there is only one orthogonal invariant distribution. So it must be the uniform distribution. So that means now, by our integral geometry formula, that this is just the volume of the Veronese hypersurface, divided by the volume of Rpn. And then it's times the volume of some this divided by this, but just a constant. Okay? And what is the final thing that you do? You just compute this volume. Now there is a fact. And believe me, it's really a one-line computation, is that the volume of, in fact, I said it this way, that this Veronese embedding is a dilation of factor square root of d. So that means if you take a unit tangent vector here, you take the image of the differential of this vector under this map, you get a vector which has length square root of d. So it's really a dilation of this. And because it's a dilation, well, the volume of this is just d to the n over 2 times the volume of Rpn. So this ratio is just d to the n over 2. So if you have a manifold, and you take its volume, scale all the metric by a constant lambda. The volume scales by lambda to the dimension of the manifold. And this is what's happening here. But I like having this fact stated this way because this is true also over the complex numbers. But now the dimension of complex projective space, it's not n, it's 2n. So the matrix scales not by square root of d to the n, but square root of d to the 2n, which gives the volume. So out of this, we derived that the volume of the image of the real Veronese, it's d to the n over 2 times the volume of RPN. But the volume of the complex Veronese same argument, it's going to be d times the volume, d to the n, sorry, times the volume of CPN. Because you're scaling by square root of d, but in 2n many directions, okay, which is the dimension of complex projective space. And this identity, by the way, also proves, running the same argument, this sort of like, it's a way for computing the Bezout number, okay? Maybe I'll just conclude with a couple of comments. So one comment, which is what I wanted to say, it's about the BKK theorem. So if you have now some, instead of studying equations where you have the full support, you just constrain yourself on choosing for each equation just some monomials, okay? You get this Newton polytope, call it P. You can argue in the same way and replace the Veronese embedding with the Veronese using the chosen monomials, okay? And then the problem just reduced to compute the volume of the image under the Veronese of just some of these monomials, okay? And you can use some symplectic geometry essentially to prove that this volume, so you take the corresponding Veronese, let me call it E, this is PE, and E is the support, just a bunch of powers. You can take the image of C star to the n, take its closure, and you can compute its volume. And this up to a constant, so it's volume of CPN times n factorials times the volume of the Newton polytope. And if you use this identity, which is related to symplectic geometry, you can prove the BKK. And maybe last thing I want to say, it's just something to introduce the next lecture. It's just a speculation today, and it will become more mathematical in next lecture. So if you think about, it's the last minute, Slava, just I want to let the audience speculate. If you think about the complex result, right? The complex result for the Bezout is the generic number of points of intersection is d1 up to dn, okay? So this number, you compute it in a ring. So how do you prove in somehow? You just take the cohomology ring of complex projective space. You prove that a hypersurface is Poincare dual to some, okay, you take the Poincare dual of some hypersurface of degree d, turns out to be d times the Poincare dual of an hyperplane, and then you just have to intersect a bunch of hyperplanes. The d factors go out, and you get d1 to the n. I just want to say that Bezout, or intersection theory over the complex numbers, it's usually cohomological. Not usually, it's cohomological, okay? It has to deal with computing intersection of cycles in varieties, okay? Their computations are happening in a ring. These cannot be cohomological, because your zero set can even be empty. You can turn it into cohomological working with Z2 coefficients, but it gives no information. But I want to argue that there is a ring where this computation is happening. So it's not going to be a cohomology ring. It's going to be a ring made of convex bodies, but it's possible to build a ring in which these computations are happening. This is what I want to argue in next lecture. Okay, I will stop here.